In this lesson, I'd like to go over arguably the two technically most challenging concepts or techniques in this course, and that's integration by substitution and integration by parts. So I want to give you a little bit of more background and so hopefully some helpful tricks and tips how to tackle these techniques. So let's start with substitution. In a nutshell, substitution is the inverse of the chain rule. So chain rule is a technique for finding derivatives. Now we've seen through the fundamental theorem of calculus that integration is the inverse operation to differentiation in many ways. So with respect to this sense of inverse, substitution takes you back from the derivative to the original function, or from a function to the antiderivative. Or it should rather say an antiderivative, because of, as we saw last time, the antiderivative isn't only defined up to an additive constant. So the chain rule is a rule that applies to finding derivatives of functions that are compositions of functions, like f of g of x here, right? So if I apply derivative to this function d dx, I'll get f prime of g of x times g of prime of x. So for finding derivatives and applying the chain rule, the crucial thing was finding the outer function and the inner function. Once you had determined what the outer function was and the inner function was, you pretty much could apply the chain rule, right? You computed the derivative of the outer function, plugged in the original inner function, and then multiplied it by the derivative of the inner function. Note also that usually the chain rule leads to kind of a more complicated expression. So this, if you compare this expression to this expression, it seems clearly more complicated. So the idea of substitution is that we now take an expression of this form, right, and apply integration to it, right? So an indefinite integral, and we will get the original function of or a function of this form back, plus a constant. So it would be f of g of x plus c. So on the one hand, it's nice that, right, we kind of have a reduction in complexity, right? If we have, we kind of reduce a complicated expression to a seemingly more simple one, right? Because, well, it just collapses to like one composition of function instead of a composition times a function, right? So that's nice. On the other hand, the problem is, well, for the chain rule, it was already often a problem determining what is the outer function, what is the inner function. Now we actually have to determine, is our integrand, right? So is the function whose indefinite integral we want to, or antiderivative we want to find, exactly of this form? Because, right, that's when the chain rule works, right? It has to be of this form, right? So that's the biggest challenge of the substitution rule, is to check or identify whether a given function that I want to integrate is of this particular form. Let's start with a simple example. So this here, right? So when you start checking for whether you can apply substitution, well, you will first check, well, is the function of the form of a product, first of all, right? So it must be a product of two functions in some way, right? Because that's what we need. We need f prime of g of x times g prime of x. Right? So here we see it's a product, and it suggests itself, right? Here's one part of the product, here's another part of the product. So once you have done that, you look at the factors of the product, right? So we have, on the one hand, 2x, and we have e to the x squared. Now you see, can I write one factor? Is one factor of the form, well, an outer function, right, times an or an outer function of an applied to an inner function, right? And maybe is that other factor that you'd have then the derivative of that inner function. And in this case, it should not be too hard to see that here you have something like e to the something. So our outer function, right? So f would be e to the something, right? And then we see the inner function, right, would be g would be, so that would be g, in that case, x squared, right? And we see here, well, the derivative of x squared is 2x, right? And that would be g prime. Oh, that's great. It's precisely of the form that we need. So here, I should rather say e to the x squared, so that would be our f prime, right? Because we have to assume it's given of the form f prime, and we have to find f then. So we would write f prime would be e to the w. So we choose a different variable now to actually then make this distinction clearer. So this is our outer function now, e to the w, right? And then g is our inner function, x squared. So x squared gets plugged in for w here, right? And then the whole term is multiplied by g prime. So it's exactly of the right form, right? So it's exactly of the form f prime of g of x times g prime of x. And once you have done that, right? So we know now by the inverse of the chain rule, right? If we integrate this, right, we'll just get f of g of x plus c. Okay, that's nice. So what is actually then left to do for us? Once we have identified this form, right? Once we have identified f prime and g, right? So outer function and inner function. Well, the only thing that's left for us now, if you compare these two expressions, well, what do we need to know to get here? Well, we need to know g, but g we have already identified as x squared, so that's great. And we need to know f, right? And that's what we don't know. So we know f prime, right? So we need f. But in this case, it's very easy because f prime is e to the w. So it's exponential function, a pure exponential function. And there we know the antiderivative right away because it's just e to the w again, right? So in our case, the whole thing would be just e to the x squared, right? So antiderivative of f prime is again e to the w. Now we need to just plug, once we have that, we just need to plug in g of x again, right? G of x is x squared, so just plug it in. That's our solution. And here's an important tip for exams and quizzes. For indefinite integrals, so for if you're asked to find indefinite integrals, you can always check your solution, right, whether your solution is correct, by just computing the derivative here of what you came up with, right? And if you take the derivative, it must agree with the function you started out with, right? So you can always check solution by computing the derivative d dx. Right, so in this case, you would just take this function, e to the x squared, compute the derivative. You see, well, that's the case for the chain rule, right? And it's e is the outer function, x squared is the inner function, right? And now applying the chain rule, I would get exactly what we started out with, because first I take the derivative of the outer function. Well, that's just e to the x. So we have e to the x squared, and then multiply it by the derivative of the inner function, which is 2x. And if you see, that's exactly what we started out with. So you can always check your work, and that's assuming, and I think that is true for most people, that they find taking derivatives or differentiating easier than integrating. So you can always take the derivative of what you came up with and see if it agrees, if that derivative agrees with you started out with. So going even further, right, with respect to quizzes and exams, so it's almost cheating, but of course there's nothing to prevent you from doing that, and so it's perfectly legal. If you don't know how to compute an indefinite integral, right, you can just look at the 5 choices that are given to you, right, and compute the derivative of all of them, right, if that's what you can do, right, and check which one actually gives you the function whose indefinite integral you're asked to compute. So just a little hint or trick here. So before we do more examples, I wanted to go over this crucial step, or practice this crucial step, identifying whether the integrand is in the right form. So right form meaning it has to be of the form f prime of g of x times g prime of x. Right. So of course, when I write f prime, that's just reminding us that in the end we have to find the antiderivative of that function. Of course, it has to be of the form some function or outer function applied to an inner function, and then it has to be multiplied by the derivative of g prime of x. So I'm going to go now over a number of examples step by step, and I think the best thing for you would be to, after I write down the example, you pause the video and try to answer it for yourself first, right? Whether this is of the right form. So let's start with the function e to the x squared. That's all. And we want to compute the integral of that. Is it in the right form for substitution? You see, can I write it as, right, in this form? And you see, well, it doesn't seem to help, right? Because it's not a product, right? So there's no multiplicative term that could be g prime of x. Here, it seems it's nice. It's like a composition, e to the x squared, right? But there's no term g prime of x. So, no. Next one, let's look at sine x to the third plus 4 times 3 dx. I should write dx here, of course. Can we use substitution here? Well, let's take a look. This seems to be nice, outer function, inner function. There is a product, right? But it turns out this factor here is not the derivative of the kind of inner function we would have in mind, right? So the outer function is clearly sine. The inner function then would be x to the third plus 4, but 3 is not the derivative of this. So again, answer would be no. Substitution is not possible. Next example, sine x to the third plus 4 times x to the third dx. Is integration by substitution possible? Well, let's take a look. We have the same function here and here, So again, it suggests that sine is the outer function. That would make x to the third the inner plus 4 the inner function. We have a product of an actual non-constant function here, x to the third, but it turns out, well, it's not the right exponent here, right? And so that's not the derivative of this one again. So there's nothing we can do here. So again, answer would be no. Well, you're probably thinking now, why do we even learn this when it's never applicable, really? But it turns out substitution is applicable in a surprisingly large number of situations. But let's go on with our examples. What about x to the third over x to the third plus 3 dx? So now, again, we would have to see what would be the outer function. Well, in this case, we would think of the outer function as 1 over something, so 1 over w, right? And then the inner function would be x to the third plus 3, right? So now we would have to have that the second multiplicative term, so whenever you see something like this, right, it's often very helpful to rewrite it as 1 over x to the third plus 3 times x to the third. So you really see the product structure here better, right? Because now you see, well, here's our inner function, x to the third plus 3. Here's the other multiplicative factor, right? X to the third, but again, it's not the derivative of the inner function. So again, once more, our answer would be no. Well, let's do another one. Let's see. We would do 4 x to the third over x to the 4 plus 2 dx. And now we see, well, it actually works this time because, right, again, the outer function would be 1 over w, right? So if you write this again as 1 over x to the 4th plus 2 times 4x to the 3rd, right? So if the outer function is 1 over w, then this would make this the inner function, right? X to the 4 plus 2. And now if you take the derivative of this, so d dx of this would be 4x to the 3rd. And that's precisely our multiplicative term. So integral, a substitution is applicable here. And now all you would have to do, since you've already figured out the inner function, just find the antiderivative of the outer function, right? 1 over w, right? And plug back in the inner function. Well, let's do some more examples. Let's do this one. It's really important. I think this is the most important step when learning substitution. Right? Identifying and check whether it's in the right form and identifying the functions involved. So let's look at the previous function a little bit, a slight variation of the previous function. So x to the 3rd over x to the 4th plus 2 dx. So same idea now, right? So outer function would be 1 over, right? So it would be f prime would be 1 over w. That would leave us with the inner function, this, right? G would be x to the 4th plus 2, and that would make g prime 4x to the 3rd. Well, now we see something interesting, right? Because, right, if we rewrite this again in this form, 1 over x plus 4, x to the fourth plus 2 times x to the third, we'll see here, well, here everything is fine, right? Everything is nice, is 1 over our inner function, and the derivative, it's so close, the other factor is so close to the actual derivative, right? It's x to the third, so the exponent here is right. The only thing that's missing is that constant here, right? So before we never were that close. We just had a constant, our exponent was completely off. It's either the factor was not there at all, or the exponent here was completely off. Now we're almost there. It's just this multiplicative constant. And in that case, so before we say no now, in that case, there is something you can do. So if you're only off by some multiplicative constant, there's a little trick you can do. So in this case, so look at this. So here's the trick. We rewrite this as 4, right? So we kind of sneak in the constant that we need, right? So we rewrite this as 1 over x to the fourth plus 2 times 4 times x to the third. So we snuck in this constant that we need. Of course, we cannot just do it without kind of giving an offset somewhere else. So we multiply the whole thing just by 1/4 at the front, right? And so now the integral would become, right, 1/4 times 1 over x to the fourth plus 2 times 4x to the third. And now we see over here, that's just, everything is the right form now for this expression. Oh, I forgot dx again. Everything is of the right form. Okay? We just have this additional multiplicative constant 1/4 here. But when it comes to integrals, multiplicative constants don't really bother us. We can just simply rewrite this as 1/4 times 1 over x to the fourth plus 2 times 4x to the third dx. And now everything that is now inside the integral is of the right form. So now this is okay. And we just computed. We just must not forget that in the end, we have to multiply the whole result we get. So the function that we get, we have to multiply by 1/4. But that's all there is, right? So that's a neat trick. So if we are off by only a multiplicative constant in our form check, right, or in our format check of the integrand here, then we can help ourselves by sneaking in the constant and offsetting at the same time in the front. So this helps also if we actually have the wrong constant. So look, for instance, at this. So we have 5x to the third over x to the fourth plus 2 dx. So in this case, right, again, we would have our outer function 1 over w. The inner function would be this, right? G of x is x to the fourth plus 2, and again, g prime, as we computed before, would be 4x to the third. Now, if we compare this with this term here, right, we see this is the wrong constant. Before, we saw the constant was missing at all, and we just snuck it in and multiplied by 1 over the constant, and that helped us. Well, here now it's the wrong constant, but it's actually no different, or not really different from the previous situation. We can do the same thing now by just saying, okay, we rewrite this as follows. Right? We rewrite this as first we pull out the constant that we don't need. Then we introduce the constant that we actually want, namely 4, right? And offset again. So this would be 1/4. So 5 times 1/4, 4 to the x, 4 times x to the third over x to the fourth plus 2 dx. Right. So in this case, we had to sneak in the constant. First, pull out the constant that we didn't need, right? So the wrong constant, we pull it out in front of the integral here, and then we introduce the right constant and do the offset. So it's just a little bit an extra step, but not much. So now here, this is in the right form. We can go ahead, compute the integral, and then we just have to remember to multiply by this 5/4. So let's finally go ahead and actually compute this integral, right? Here we have now our outer function f prime plus 1 over w. So now we need an antiderivative of this, right? So that what is the antiderivative of 1 over w? Well, that's ln w plus c, right? Antiderivative of 1 over w is ln w. And g, we already have identified as x to the fourth plus 2. And the derivative of g we can actually drop in the will vanish in the integration process. So all we are left with is now our constants here, 5/4 times ln, right, outer function, and then plug in the inner function, so x to the fourth plus 2 plus c, of course. So let's go over 2 more problems. Let's do these from the book. So this is 6.6, number 2, and number 4. On Piazza, you'll find already a detailed solution for number 3 and number 5. So there's more if you prefer to read over things. So I posted a detailed solution there. So let's look at number 2 first. So number 2 is integral x times 1 minus 5x squared d to the fifth dx. Okay. So is substitution applicable here? Well, again, first thing we do is try to identify inner and outer function. So again here, this seems to suggest that there is an outer function present of the form, you always use blue for the outer function, so f prime of w is w to the fifth, right? So because this whole term is just like w to the fifth. So the inner function now would be this. G of x is 1 minus 5x squared. So that would give us g prime of x as minus 10x. And we see, well, what is the other term here that's available? It's x. Now we compare this with g prime of x, it's minus 10x, and we see we're only off by a multiplicative constant. So the answer here would be yes, if we do this trick now to sneak in the right constant again, right? So to compute the integral now, we would do the following, right? We would multiply by minus 1/10, right? And then we would have minus 10x times 1 minus 5x squared to to the fifth dx. So all we need to do to compute the integral now would be to find an antiderivative of this function w to the fifth, and using the power rule, that's actually easy. So f of w would be 1/6 w to the 6th plus c. And now we just plug into this function our original g, so we would have that this here integral is then actually 1 minus 1/10 minus times 1/6 is 1 minus 1/60th times, and now we plug this inner function back into here. That would be 1 minus 5x squared to the 6th plus c. And again, you should always check your result by actually computing the derivative of this. So please do this here and see that we actually get this. So if I made a mistake, please let me know. So let's do number 4. That would be x over square root ln x dx. Again, with these in these forms, cases, it often helps to rewrite this first, the integrand first, as 1 over ln x times x. Right, so now it should be clearer what might possibly be the outer function, what the inner function, right? So outer function, I would say, is 1 over square root, right? So f prime, in this case, would be 1 over square root of w. Inner function would be then g would be ln x, and g prime would be, well, 1 over x. But now we compare this again. Is this a factor here? No, it's x. So, but we need 1 over x, right? So, and they do not differ by a constant, right? So instead of 1 over x, we get x, but the two expressions do not differ by a multiplicative constant, right? So in this case, we have to say no, it's not possible. So you may ask now, well, if we cannot use substitution, what should we do to compute an integral like that? Well, there is one more technique, which we'll turn to now, integration by parts, but often that is also not applicable. So it actually happens that sometimes functions, the integral has no what is called closed, or the indefinite integral has no closed form. So you cannot really write down a nice function that would be the antiderivative. Then often you have to resort to numerical methods if you want to compute a definite integral, or other approximation methods, which unfortunately are beyond this course. So, but you can rest assured that in this course and in exams, you will only get problems that you have the means to solve. That means the techniques. We learned the techniques to solve them. Okay. So we turn now to integration by parts, and while the integration by substitution is the inverse to the chain rule, integration by parts can be seen as the inverse to the product rule. So the basic idea is that if I have a product of two functions, if I apply the product rule and compute the derivative, that would be f prime of g plus f times g prime. Now, if I take the inverse, right, if I integrate now, right, so I integrate, so if if I start out with this and I integrate, right, I get the original function back, f times g plus c, of course. But what I want to write now here, so let's write this in a more detailed way. So we can write this then as f prime of g plus f g prime, right, will give us f times g plus c. Now we can rearrange this so the integral is what is called additive. So if there's a sum, I can spread out the interval, distribute the integral over the individual terms in the sum, right? So I can write this then actually as f prime g plus integral f g prime is equal to fg. So let me just, forgive me if I drop the c now for convenience. So what we can do now is we can bring one of these terms over to the other side, right? Right. So let's say we bring this one over to the other side, and that would then give us, so let me just write this here in the center. So this would then give us f g prime, right, is equal to fg minus integral f prime g. Okay. So far so good. But what is this good for, right? So why might this rewriting this whole thing to end up with this be useful? It just seems to be a rearrangement of terms. So why would this ever help us to compute integrals? Let's rewrite this here. So why would this help us to compute integrals? Well, the thing is, you always have to think of, okay, let's assume this is given, right? So this is the function that we are given, and it is given as a product of two functions. So then, right, to compute this integral, the right-hand side tells us that we have to find the antiderivative of g, right, and have to define the derivative of f, and then find the compute the indefinite integral of this. Note that the one thing that it helps us in, or could be helpful for us, is that it might be easier to find g, right, and f prime of integral of f prime times g, right? Because those are the two things that we would have to find in the right hand side. Those are the things unknown to us. This is given to us now, we assume. Then we would have to find g, and we'd have to find this. So it's not really clear why that might be the case, but often it happens, because when you take f prime something and multiply it with g, and you find g, and you take this product, something happens to this product that all of a sudden makes this integral very easy to compute. So it might be easiest to go over an example to see what I mean by this, how this could be helpful. So it's 6.7 problem 12. Right, so it asks us to compute ln x over x squared dx. Okay. So first note that substitution is not applicable here. I mean, we could try to say, okay, here we have the outer function 1 over w. That would make the inner function x squared. The derivative would be 2x, but the multiplicative factor here is ln x. Right. So substitution doesn't go anywhere here. So let's rewrite this as follows. only as ln x times 1 over x squared. And remember now the formula. So let me put this in here. So a little box. So f g prime fg minus integral f prime g. Okay. So integration by parts tells us that we can compute this integral, right? If we can write it in the form f g prime and then compute the right hand side, right? So the problem for integration by parts is often, okay, to decide, well, I have a product, now which function should be f and which function should be g prime, right? That's the kind of fundamental decision you have to make, because it's, well, you could flip these around. It's not automatically that the first function should be f and the second function should be g prime, right? So that's it really depends, and you have to check. Sometimes you have to check both possibilities, making the first function f and the second function g prime, or making the second function f and the first function g prime, and so on. So sometimes you have to do that. And there is an example on Piazza. I think I go over, it's 6.7, number 9, I think. Yes, so 6.7, number 9 on Piazza. 6.7, number 9, where I think I go over both possibilities and only one works out. Well, in this case here, we have to, well, if we declare one function, as soon as we declare one of the functions of g prime as g prime, we have to be able to compute the antiderivative for that function. And here, in our case, well, do we know an antiderivative of ln x? No, we don't know that yet. But we know an antiderivative of 1 over x squared, right? So let's do that. So let's declare this is f and this is g prime. Okay. So then what we'd have to do now is to compute an antiderivative of g prime. So let's do that. So this would be by our formula ln x times antiderivative of 1 over x squared. So this is the same as x to the minus 2. Now we can use the power rule for antiderivatives. So that would be minus x to the minus 1. Right? And now we have to subtract from that f prime. Now we need to compute f prime, but that we know how to do, because ln x, well, that's 1 over x. And then take what we have here, minus x, so g, right? G is this here now, right? So we just write this here again in this integral. So that would be minus x times minus 1, so it would be minus 1 over x, right? I always forget the dx, so I hope you don't mind it. But formally correct, it needs to have a dx. Okay. And then of course there's the plus c, but I hope you really forgive me that I don't carry this along all the time now. Okay. So let's write this a little bit, clean this up a bit. So it would be minus ln x, x to the minus 1 would be 1 over x, minus, and now here we have minus, we can pull this out of the integral, and it will be 1 over x squared dx. But now we see what actually happens, and that's precisely what we had in mind when we started out, where the power rule might be helpful, right? Because let's see what happened to this integrand here. By multiplying with the derivative of this suddenly turned into this integral, turned into a perfectly nice integral that we know how to compute using the power rule, right? And this is already there. We don't have to do anything with that anymore. This is already kind of finished for us. The only thing we need to take care of now is this. So by bringing the derivative of this into play, we actually turn this product here into a very nice product. It doesn't have this kind of hard or difficult form ln times some other function, right? It's just a single power function now. So we can go ahead and compute this again. So that would be minus ln x over x plus, and now we have already actually computed this integral before, right? It's minus 1 over x. And now I'll add the plus c. So if you want to clean this up a little bit further, you can pull out minus 1 over x. And you're left with ln x plus 1. Not to forget plus c. So once again, you see how integration by parts can work and help you, right? Because just by choosing this the right way here, you actually can hope that, well, the thing is that you start out with an integral, you get a fixed term that is finished for you, but you have another integral to compute. So the hope is that once you do this transformation, well, the other integral that you still have to compute is simpler than the one that you started out with. And that's exactly what happens here. The one thing you have to be able to, however, is once you declare one of the functions as g prime or v prime or whatever it's denoted in the book, then you have to be able to find an antiderivative for that. But we were able to do that with minus x to the minus 1. And you have to be able to compute a derivative of the f part, which usually is not that big a problem. So I really encourage you to look at the solution I posted on Piazza. Again, it's 6.7 number 9, where I really go over the details, how to pick the functions and how the possible choices make the integral, computing the integral either not possible or much easier, right? So what I want to do for the rest, or for the last part here, is to go over the comparing the substitution rule to the integration by parts rule, in the sense that I want to kind of see when do you apply what rule. So this is problem 6.7 number 23. And this asks us to say, do you use integration by parts or by substitution? So parts or substitution. Again, I encourage you to pause the video after I wrote down the function and try to do it, come up with an answer yourself, and then compare with what I'm going to say. So let's start. We have a, the function indefinite integral x squared over 1 plus x to the third dx. So should this be parts or substitution? Well, we'll see. Well, here is a nice structure again of 1 over something, right, over this. That would leave our inner function with 1 plus x to the third. derivative would be 3x squared. We see that's up to a multiplicative constant what is already there. So we see if we have everything up to a multiplicative constant, we're fine. So in this case, we would use substitution. Next problem, B, x times e to the x squared dx. We have already almost done this problem, something very similar. You remember we had the same problem where we actually here had a 2 in front. But you see now, from what we've just looked at, right, here outer function would be e to the w, e to the something. Inner function would be x squared. Derivative would be 2x. We have x there, differs from 2x only by a multiplicative constant, so substitution works again. Okay, so next one, C. X squared ln x to the third plus 1 dx. So what do we have here? Well, outer function clearly seems to be ln, right, of something. That would make the inner function 3x to the third plus 1. Derivative of this would be 3x squared. And we see we have an x squared present, which is up to a multiplicative constant, is already the same as 3x squared. So everything works for substitution. Again, they probably should have mixed up the problems a little bit better. No. Okay, moving on to D. 1 over square root 3x plus 1 dx. Okay, outer function seems to be 1 over square root of w, right? That would make the inner function 3x plus 1. Derivative would be 3. Now, we have 1 up here, right, as a multiplicative constant, but it's just a multiplicative constant off of 3, right? So everything looks nice. Again, we can use substitution. Let's go to E. X squared times ln x dx. Okay, what do we have here? It seems pretty clear right away that substitution is not applicable, right? Because, well, if there's the outer function, we could choose ln x, right? ln. Inner function then would be just x, and derivative would be just 1, but that does not help us with the factor x squared here. So it's pretty clear that substitution in this case does not work. So in that case, you would use integration by parts. Quickly, we could go over how to do this, because this is a similar effect that happens as we did when we did the problem before. So if we choose this again as f, and this we choose as g prime, right, then this would be the same as, now we have to do f, which would be ln, times g. So we take an antiderivative of x squared, which would be 1/3 x to the third. And now we have to subtract from this f prime, right, which is 1 over x, times g, which is 1/3 x to the third dx. And now you see what's happening. So this remains the same. So maybe we can write it as in this form, minus, and now we have 1/3 here. And now we have 1 over x, times x to the third. that would just be x squared dx. And you see now, again, it happened nicely that when we applied the derivative to this, so to get f prime, and multiplied it with the antiderivative of this, x squared, so 1/3 x to the third, here in the integral happens a nice cancellation, and we get to a form that we actually know how to compute, right? This integral is, again, easily solved, computed using the power rule. Right? So that's often the case if you want to tackle logarithmic integrals. If you want to tackle logarithmic integrals, that you declare the ln part as the f function, and then you take a derivative in this part, and that will kind of behave, then play, or it will play nicely with the g prime part, or the g part here. Right. Last one, f is integral ln x dx. Now this is something very interesting. I like this integral here because, well, substitution, of course, right? So what would be your outer function? Well, it would be ln, right? So ln would be the outer function, and the inner function would just be x, and the derivative of x is just 1. But this is actually 1 times ln x, right? So it is exactly of the right form. So theoretically, the substitution is possible. The problem is only, well, if you want to apply substitution, you need to be able to, right, if once you have written it in the form gx times g prime of x, right, once you've written it in this form, you have to be able to compute f. So you have to compute an antiderivative of the outer function. Our outer function now is ln, which is just the function we want to integrate. So although it's theoretically in the form that substitution is possible, it does not help you at all, because you just end up with the same thing you started out with. Okay. So then, well, why would substitution by parts here be possible here? Well, it does not seem to be in the form of a product. Well, and that's the nice thing, is this is a neat trick. You just write it as we already did here, 1 times ln x. And remember that these integrals with ln x, right, often what happens if you declare this as f and declare this as g prime, right, what happens when you later take f prime, right, it will cancel out or transform the other integral in a nice computable integral. Okay, so namely what happens now here would be, right, so f times g, right, g prime is 1, so g would be x, minus, and now we would have to take f prime, which would be 1 over x, times g, which is x, so it would just be ln x times x minus integral 1 dx. But that's a really nice integral. We can solve this right away. So this would be ln x times x minus integral 1, that would just be x, right? So we would get, simplifying this a little bit, x times ln x minus 1 plus c. Okay, so here you see sneaking in this kind of constant, right, or writing this a little bit differently. Suddenly everything works out by using integration by parts. Okay, and the reason again is that in the second integral you take the derivative of this part, right, and that makes this suddenly into a very nice integral. So I hope this lecture gave you a little bit more help with tackling these two techniques. And as I said before, they're not easy, and I think technically and conceptually they're among the really most difficult parts of this course. So I hope you find this a little bit helpful.